All right, so in this example, we're actually going to cycle back on some of these kind of weird conditional statements that are going to involve some perfect squares. So in this example, I'm going to claim that if n happens to be a perfect square, then the number that is 2 more than it, i.e. n plus 2, is not a perfect square. So in this case, we're going to see that these perfect squares start to become a little bit more spread out. So let's think about what's going on in this situation. So first off, I want to think about what does this statement actually look like in symbols. So what's going to happen is that I'm going to introduce my kind of terminology that says S of x is going to be the phrase that x is a perfect square. So a perfect square. Yay. A terribly drawn square. Okay, so my original statement is going to be of the form for all n, in this case, let's go ahead and just take positive integers. What's going to happen is that if this thing happens to be a perfect square, then the thing that is 2 more than it, that is n plus 2, is not going to be a perfect square. So that's my original phrase. So if you think about it, we know that it's kind of easy to know what it is to be a perfect square. The idea is that if I'm a perfect square, that's going to say that x is going to be some k squared. But it's hard to show something is not a perfect square. So maybe you're tempted to initially say, okay, let's look at the contrapositive of this thing, because that's going to have this nice ability to, okay, I don't want to have to deal with this kind of awkward conclusion that says not a perfect square. So the contrapositive of this thing is going to simply say for all integers, or for all positive integers. What's going to happen is that I'm going to flip around my hypothesis and conclusion, but they have to pick up negations. So what's going to happen is that this thing initially starts with a negation. When I negate it again, it's going to just introduce just the notion that n plus 2 is a positive square. But then what's going to happen is that when I flip it around, this thing is going to pick up a negation. So it's going to say it is not the case that n is a perfect square. And I'm in a sense right back to where I started. I'm going to be assuming something about something being a perfect square, but at the end of the day, the thing that I'm kicking out should not be a perfect square. And both of those situations are challenging to work with. So in this situation, we're led to maybe think about, okay, let's try looking at the negation of this thing. So let's look at the negation. So if I tried to negate my initial statement, I'm going to write this all out. So we're going to kind of see what's going on in this situation. So integer, I'm going to have s of n is going to imply the negation of s of n plus 2. Okay, so if I think about trying to negate this object, what's going to happen is that my universal quantifier we know is going to convert into an existential quantifier. So this is going to say there is going to exist some positive integer, and then I'm going to have to negate this conditional thing. And right now it is of the form a implies b, and I know that negating something that looks like a implies b is not going to be another conditional. It's going to kick out something like a and not b. So what's going to happen in this situation is that I'm going to keep the s of n, the fact that n is going to be a perfect square. That's still going to be left alone. I'm going to pick up an and from this little and then I'm going to negate this thing, which again has a negation already, but that's going to be really nice in this situation because I'm going to have the negation with the negation is going to simply say that s of n plus 2. So what's happening in this situation is that I've now removed all this information about things being not perfect squares, and that is going to be our savior. So what's going to happen is that I'm going to try to show you that this negation is in fact not true. So if I can show that the negation is false, that's going to tell me that my original statement is actually true. So what's happening in this case is that I get to assume that two random numbers, in this case n and n plus 2, happen to be perfect squares, and that there at least is one pair of those things. So what's going to happen is that n is going to look like some, let's say, h squared, and I'm going to have that n plus 2 is going to be some other perfect square. So let's just call this thing a k squared. So now I'm at the stage that I can work with these things. Somehow I want to say that this cannot happen. And now is where the kind of trickery comes into play a little bit. So this next step is a little bit of a definite trick, if you want to think about it. What I'm going to do is I'm going to take these two objects and I'm going to subtract them from one another. So that is, if I look at k squared and if I subtract an h squared from it, well, what's going to happen is that it becomes an n plus 2 minus an n, which is going to kick out a 2, which is totally fine. There's no harm in doing that. I'm just going to take these objects. If I subtract them, it's going to say that the difference between these two perfect squares is 2. And that's all this is saying, is that if I have these perfect squares, there's going to be a gap of 2 between them. And I'm going to say that that can't occur. So what I can do in this situation is I can see that there's a difference of squares occurring, and that's what's going to lead me into using this difference of squares formula. The idea that I can represent this thing as k minus h multiplied by a k plus h. So now if you look at this, what's happening is that I have two things on the left that are being multiplied. There's this object and that object, and they're both integers, and they're being multiplied together, and they're going to happen to kick out a 2. and 2 is a prime number. So the only way that I can get a 2 is if one of those things is a 1 and the other one happens to be a 2. So the question is which one is which? Well, if you think about these k's and h's are going to be positive numbers, and if I add them together, it's just going to become a larger number. So the best bet I have of making one of these things into a 2 is by looking at that second object right there. So that's to say that that thing is going to become my 2, and this thing is going to become my 1. So what's really happening is that I'm going to obtain this little system. Let's change colors again. I'm going to have that first number, k minus h, is going to be a 1, and I'm going to have that k plus h. This thing is going to become a 2. And now you can see I have a little system of linear equations, kind of going back to your college algebra days. If you add these things together, what's going to happen is that you're going to get 2k. Those things disappear, and if I add those things on the right, I'm going to end up getting a 3. Which this is going to then say k is equal to 3 over 2. And that's where the contradiction comes into play, is that when I have this notion of being a perfect square, I'm supposed to be able to find some integer that's going to say that n is equal to h squared, or n plus 2 is equal to k squared. And these h's and k's, these are supposed to live in the positive integers. But 3/2 is most certainly not a positive integer, it's a fraction. And that breaks this argument, is that on one side I assumed that this k was going to be an integer, but at the end of the day I was able to show you that this k was actually equal to a fraction. And that's where those two things are going to butt heads. And then from there I can say, actually, my negation is complete garbage, because I assumed I could do this, but at the end of the day I end up with this contradiction, which is to say that k is equal to 3/2, which then must say that my original thing must be true. So if I try to kind of come up with a slightly cleaner version of this, I'm going to let the reader know right away, hey, I'm using a proof by contradiction. And then in this case, I get to assume that kind of what that negation is going to say. So I'm going to assume that there's going to exist some integer n such that n and n plus 2 are in fact perfect squares. So since n and n plus 2 are perfect squares, there's going to exist some non-negative integers h and k such that n is going to equal h squared, and n plus 2 is going to be this k squared. So here's where the little trickery came into play, is that the difference between those two things is going to have a gap of 2. So I'm going to write 2 as k squared minus h squared, do that factorization, and here's where I'm going to say one of these things must be a 2 and one of them must be a 1. It turns out that this one's the 2 and that one's the 1. And then it gives me two little equations that says k plus h is 2, k minus h is 1. If you add them together, it gives you 2k equals 3. Dividing by 2 is going to say k is equal to 3/2, which then is going to contradict the fact that this is not a non-negative integer, which then says that the original thing must be true, and kind of clean it up from there. There are actually a few other ways to attack this result, one of which is going to be kind of piggybacking off of a result that you're going to see in your homework. So what's going to happen in this case is you end up having a bunch of little results. And in the world of math, these little tiny results are often referred to as lemmas. These typically lead towards a much kind of more grandiose theorem. So they're kind of little results that have to be proved on their own, but they can funnel into these bigger results. So the one that you're going to see in your homework is going to have this fact that says, if n is a perfect square, so if you give me one of these perfect squares, I know what these things are going to look like in the mod 4 setting. If you give me a perfect square, it's going to kick out either a 0 or a 4 mod 4. I'm never going to pick up a 2 and I'm never going to pick up a 3. So that's the kind of neat little result that you're going to see. Well, I know that I can manipulate this thing and change the way it looks a little bit. If I look at the contrapositive of this thing, I'm going to switch the hypothesis and conclusion, introduce the and by using De Morgan. So an equivalent version of that lemma is going to say that if I have a number that is not 0 mod 4 and it's not 1 mod 4, then I know that that thing is not a perfect square. So you can kind of see that that's going to give me some guidance on this kind of quest for showing something is not a perfect square. All right, so then the last kind of equivalent version of this is actually going to just piggyback off of this notion of what does it mean for something to be congruent to something mod 4. So if I know that I'm not 0 nor my 1 modulo 4 setting, I only have two other options, and that happen to be either 2 or 3. So the third and equivalent version of this I can say is that if n is 2 mod 4, and this should say or, n is going to be 3 mod 4, then I'm still going to be in this position that I'm going to be not a perfect square. So I can actually use these three kind of equivalent versions of this result to actually come up with a much kind of shorter and pretty slick version of this proof. So the idea is that if you start with some random perfect square, call it n, by that previous lemma, that first version of it, I know that n should be either 0 or 1 mod 4. And now from there, then I can break this thing up into two cases. In the first case, I'm going to assume that n is going to be 0 mod 4, and in the second, I'm going to assume n is 1 mod 4. And my goal now is to show that n plus 2 is not a perfect square. Well, if I look at n plus 2, I know that n plus 2 is then going to be congruent to 4 mod 4 in the first setting because I start with that, and adding 2 is going to leave me at 2 because I started at 0, and then 0 plus 2 is just 2. So I know that n plus 2 is going to be 2 mod 4, so then that previous lemma is going to in fact tell me that n plus 2 is not a perfect square. Likewise, in that last case, if I start with n being 1 mod 4, if I add 2 to both sides of that thing, I'm going to see that n plus 2 is 3 mod 4. And again, an application of that previous lemma is going to tell me that n plus 2, well, it's going to be living in this 3 camp, which is going to tell me that this thing is not a perfect square as well. So like I said, that is a very slick kind of secondary proof of this thing. It did rely upon some pretty, I guess, kind of interesting little lemmas on their own regard and things like that, and the ability to kind of bring these together is going to kind of show you that you don't have to go through these kind of horrible contradiction approaches. You just sometimes have to come up with a little bit of machinery to actually get to the result that you're looking at.